Hello, I'm Neeraj. Welcome to the second part of this tutorial. In the second part, I will discuss about batch normalization. So let us start. Actually, in the traditional architecture, deep learning architecture, we generally use input layer and multiple intermediate layers and then output layers. And what happens? We pass the data from one layer, like suppose this is the output of this layer, we pass this directly to as an input to this layer. But with the case of batch normalizations, we are not doing that. We just take the output of this layer and pass it through some batch normalization function, and it generates some value, and we pass this value to this layer. So this is the difference in the forward pass that we observe when we use the batch normalization technique. So how we achieve that? For that, we just take the batch, mini batches. Suppose here we took the mini batches of size m, and then other merits of plus point of this batch normalization technique is we have some learnable parameters also. Means this is not a constant thing that we pass it every time we pass it through some value and then it just upgrade it to some value. Means it adds some learnable parameters also. The major benefits of those learnable parameters are every time based on the updation on those learnable parameters, every next time we can get the more sophisticated output to the next layer, and it generally helps in better convergence. So here you can see that output is Bn, batch normalization, gamma, beta, xi. So same we have used to pass it through the next layer. Now to calculate this, we calculate something. First we calculate the mini batch mean. So mini batch mean 1 divided by batch size into summation of I equal to 1 to m, and then xi is the data of mini batches. And then we calculate the variance also in the same way by dividing 1 by m, and then I equal to 1 to m xi minus mu b whole square. So this is the way we calculated the variance. Now we need to normalize this because without normalizations I think it will take more iterations, and I think again it will create the convergence issues. So we normalize it by dividing it by root under sigma b square plus epsilon. Epsilon is just a small value, a small means a variable having a small value greater than 0. The main role of this variable is to keep to avoid the chances of division by 0 if this part is 0. Now the next part is to properly define that how we can generate the batch normalization output. For that the authors has taken two things, two learnable parameters, gamma and beta. So the output depends upon the gamma into x bar I calculated from here plus beta. So this is used for scaling and shifting. And gamma and beta is learnable parameters. All the variables used in this algorithm is differentiable. This means at the time of backpropagation, we can compute the derivative of loss function with respect to all these variables. So authors in the paper, they have given how we can compute the derivatives. So they have calculated the derivative with respect to loss. L represents the loss. So derivative of loss with respect to x hat I, and that is derivative of loss divided by this into gamma, because this is 0, because this portion will be 0. Similarly, we can compute the derivation of loss function with respect to sigma b square, derivation of loss function with respect to mu b, with respect to xi, with respect to gamma, and with respect to beta. Here we have used this and this derivations with this to compute this and this. So for all those computations, we directly put the value here from here and here and here. So that's why we got those variables. This is very easy to understand. I think you can go to the paper and plainly understand. So now with the differentiability, it means like when in the backpropagation the system will backpropagate and learn the other network parameter. It will in the same time it will learn those parameters also, and it will be the part of the backpropagation. So that's why due to those backpropagation support and differentiability, it generally gives the results in less number of epochs. It means easily converges. But like other model, these models also has a lot of merits and demerits. So merits I already discussed. Demerits are like you can understand from this algorithm. As you have seen that we are taking the order of mini batches, and then we do all the computation one by one. So each time one mini batch we will load it for forward pass, next time next mini batch we will load for forward pass, and then back propagation. Then it will due to this ordering, it will have some sensibility towards the ordering, and it may affect the performance also. So quick remedy for this may be like using shuffle batch normalization. Means shuffle the input and then use the batch normalization. Second problem that you can easily understand, that we are using mini batches. Suppose the size of mini batches are too low. In that case, that mini batch will not represent your data distributions. So in that case, using that batch normalization with that mini batch sizes will not give the sufficiently good result. Next, suppose you take very high size of mini batches. Even in that case, the system will not converge. Generally what happens in the batch normalization cases, we use the batch size greater than 16. Otherwise, in a lot of practical experiments, it is observed that it is not working well. Other problems that you can easily observe, that instead of passing in a forward pass, instead of passing this input directly to the next layer, we apply this arrangement, and we use this arrangement in backpropagation also. Means we are using external overhead for the entire training. So this is another demerits. Next demerits may be it will not work with, it is generally not working with RNN and GAN architecture, RNN, LSTM, GRU and GAN architecture. If you use it here between two RNN block, then it will destroy the network. But suppose you are using the RNN block like this, and you use the last hidden layer output, and here you can apply the batch normalization, then here it may work. So in RNN, if you want to put something here, then for that there is a recurrent batch normalization system. And similarly for GAN also we have something different arrangements. So this is the plus and minus point of all the batch normalization system. So in the next tutorial I will try to explain about layer normalization, weight normalization, group normalizations, their merits and demerits, and some new research directions.